Get started. Welcome to today's HAO colloquium. Very happy to have Professor Fran Bagenal here. Fran came to the U.S. Inspired by NASA missions, Mars, Voyager. So he went to MIT and got her degree there, working on Voyager plasma space experiment in Jupiter's giant magnetosphere. I was just joking with Fran. I looked at the website of the Voyager plasma science experiment. First, it's in the museum setting in MIT, and it looks awfully like the Darth Vader's mask. And so she then went back to UK, working as a postdoc at Imperial College, and then the Voyager flybys of Uranus and Neptune brought her back in '89, and this time back to Boulder, where she's now professor of astrophysical and planetary sciences, and also a research scientist at LASP. In addition to Voyager, Fran has been involved in science teams of Galileo mission to Jupiter, and also Deep Space 1 to Comet Borrelli. She leads the plasma teams on the first two New Frontiers missions, New Horizon, which we'll discuss in details, and Juno, which will get to Jupiter around July 4th this year.
Okay, thank you very much. And of course, you missed the most important thing, which is I spent a year here at HAO in 1987. So before I started on the faculty. I never recovered, indeed. So it's great to be back. And so I'm going to talk about New Horizons mission to Pluto. We'll have a little bit of space physics, but basically this is just about a lot of fun thinking about this very strange little world. So Pluto, we need to sort of step out many steps out to the outer solar system and think about its orbit. It takes a long time to go around the sun. It hasn't even gone halfway around since it was discovered in 1930. And very important for getting a mission started is the fact that the second Kuiper Belt object was discovered in 1992. So back in 1989, I started working with Alan Stern when I was a junior faculty at CU. And to get a sense of how long ago this was, we had a celebration of the perihelion on campus, and we were allowed to drink beer on campus. I mean, that could never happen now. Anyway, we started working on this mission, and it took us a long time to get started. But this discovery of Kuiper Belt objects was very important, because if you look at this movie that has put together, this is Pluto and now other Kuiper Belt objects discovered as this is as a function of time. You can see the discovery looking in directions and discovering various Kuiper Belt objects. You can see we've now got a couple thousand of these things, some of them quite large. Also note the gap here. Observers, why is there a gap there? Why have we not detected them here and here? Milky Way, absolutely. Hard to see them there. Very important that that's the direction we're heading in Pluto. The other point I want to make with this movie is the fact that these are scattered. They are not in the ecliptic plane, they're above and below. And of course, has a lot to do with the origin of this system. So these Kuiper Belt objects are very different colors, different shapes. Some of them have moons, some of them don't. But notice the scale here. These are on the order of 1,000 kilometers, these larger ones. There are many more much smaller. And for comparison, the largest asteroid belt object observed by NASA's Dawn mission is comparable in size, if a little smaller. So when we started thinking about this mission to Pluto, I was thinking something that would look like this. I was expecting an object that would be covered with impact craters and not a whole lot more. That was my expectation. And many of the others on the team too, I think. So let's think about the scale. Here we have Pluto and Charon, the moon that is, this is really a binary system because they orbit around each other. Binary system. This is actually a fairly realistic in terms of mass. So you can see the center of mass is about here. And they are spin phase locked. So they go around like this, around a center of mass, every 6.4 days. Okay, so that's a fairly realistic scale. And what's important, though, is to think about this in relation to the scale of the Earth. So these are much smaller than the Earth. This is about the right separation and the right size. And then when you look at the masses, Pluto, there's 457 Plutos in the mass of the Earth, and the ratio of Pluto to Charon is about 1:8. So that gives you a sense of the scale of the system that we're looking at. Now, what did Pluto look like before we got there? Well, the best we got was from Hubble and from ground-based observations, and you can see we couldn't really resolve much of the disk. We saw some dark regions, some light regions, but you can't do geology with this picture, right? You have no sense of what it looks like. We did know that Pluto was a little brownish, whereas Charon seemed to be grayish, and we did know the temperature, which is bloody cold, whatever units you use. And then the density is about 50-50 rock and ice. Okay, so we started working on this back in 1989, Alan Stone and I, and we had a whole bunch of studies that were done of missions to Pluto. And what's important is to think about what was happening at this time in terms of designing missions. NASA was struggling with whether do we have large center-led missions or PI-led competitive missions. And we needed to get support from the National Academy, the decadal surveys, to get a mission to somewhere in the solar system. And what's interesting is that at first, a lot of people said, why go to Pluto, who cares? But as the Kuiper Belt objects were increased in number, it became important that people realized this really was a place that we should go, not to just check off Pluto on the list of objects in the solar system, to really understand how we got all these objects scattered out in the Kuiper Belt and look at the larger one for comparison. So we designed a mission that was small. This object is about the size of a small piano. This is the radioisotope thermoelectric generator, the plutonium-238 powered power system. Provides about 200 watts. This is our 6-foot dish that sends signals back to the Earth. This is the radio experiment, which was doing occultation measurements of the atmosphere and ionosphere. Then we have cameras, the long-range LORRI camera here that has high-resolution black and white pictures. I'll show you some of those. RALPH includes a wide angle and a color system. Looking at spectroscopically, looking at the composition of the surface. We have a UV instrument that is designed to look back at the sun and do solar occultations of the atmosphere, very important. And then there are a couple of particle instruments, high energy particles and low energy particles, that measure the solar wind and the interaction of the solar wind with the atmosphere. And then most important is the student dust counter. Designed, built, tested, operated, and the data analyzed by students at the University of Colorado. And so what this is this is about the actual size of the instrument. It's pieces of plastic, very special plastic, that detect micron-sized particles that are streaming into it at about 14 kilometers a second, or 33,000 miles an hour, producing signals that tell us the frequency of dust that's being gathered as the spacecraft is flying through the solar system. And this tells us how much material, how much dust is produced by the breakup of objects in the outer solar system, and get a sense of the grinding down of material in the solar system. Okay, so I want you to guess, how often do you think we get signals from the student dust detector as we move from 1 AU out to 33 AU? On average, what sort of signal rate do you think we get? I want you to make a guess. What do you think? 1,000 a second? 10 a day? 1 an hour? 10 a day? Any other guesses? 5 a year? Wow, that's quite a range, huh? 1 every 3 days, right? So it's not a huge rate, right? But important for understanding, the amount of material. It shows you that space is pretty empty. Yeah. Okay, so eventually we launched the spacecraft back in January of 2006. But just before we were about to launch it, Hubble detects 2 more moons, and then on our way out there, we find another 2. So here we are, we have 4 little moons. We have Pluto and Charon. We have 6 objects to study. And then all of a sudden, we're beginning to think, uh-oh, what if these little moons are produced by a recent impact that has produced a cloud of debris? Are we going to see that debris as we approach? Usually you see dust when you have light behind, not light behind you. Light behind the object that you're seeing, right? So you see, as you go through fog, you shine a light through the fog, you see the fog. But if you're going the other way, you can't see. And so we were worried that we were going to be ramming into a whole bunch of dust. And then after a 9.5-year travel out to Pluto, the spacecraft would die before we got the data back. So this was quite a major concern that we had to deal with. Because this journey is a long one. We saved 3 years by getting a gravity assist at Jupiter, but even so, it was a 9.5-year journey out to Pluto. Okay. So as we approached, the pictures got better and better. And the geologists were like, ooh, I think I can see a crater. Ooh, maybe that's a, and the rest of us were saying, it's a fuzzy blob. But eventually we got good pictures. And this was a great picture. All of the particles and fields teams were jumping up and down and getting excited. And guess whose pictures got in the newspaper? It wasn't the geologists, it was actually the particles and fields people. But, we showed our enthusiasm, even though our data wasn't down yet. Okay, so let's talk a bit about the data coming down and what was involved. This really is a robotic mission. And I think it really brought home to a lot of people this idea of robotic missions, because you have to see the duration of this flyby is 4 hours, okay? And these are 10-minute ticks. But you have to realize that it's a 4.5-hour one-way communication time. So there's no way you can joystick. There's no way we could change the trajectory. And furthermore, this little spacecraft had to go make all its observations and then turn back and look at Earth. So this is a little 10 minutes compressed to a second. The observations, this is from Eyes on the Solar System, and you can see the observations that have to be made is a really complicated sequence of about 9 hours of observations that we pre-programmed into the spacecraft. We had tested it beforehand, so we knew that the program would probably work. And we had to design this and tell the spacecraft, go do all this, fill up your memory storage, and then communicate back with Earth. So it's very much a robot off doing its own thing, out of direct human control. Okay. And so we designed this very carefully. So you have to remember that, of course, if it's 33 times further away from the sun, it's going to be 1,000 times fainter sunlight. And so we had to think about where we were going to fly by. So if I just go back a couple here, you'll see that we are actually about 9 Pluto radii away. And that was designed to be a very specific distance, and then the trajectory is designed so that we have both a stellar and Earth occultations of both Pluto and Charon. Okay, so what we designed is a distance so that we would be able to get decent pictures, fairly long exposures. So these are maybe a 10-second exposure, but we're moving really fast, so we didn't want to. If we got closer, we'd have very blurred pictures, right? And you get further away, you have less resolution. So you have to optimize your distance so that you get clear pictures and not have them blurred with fairly long exposure times because of the weak amount of light. I mean, of course, we could carry a bigger camera, but we were very mass limited in order to get out to Pluto on as fast as possible. So this was optimized, and we got these pictures, and we all cheered. But then we had to sit and wait. And what do you do when you have to wait 9 hours for your data to come in? Well, we took selfies, right? I mean, actually, we had a great time. There were all sorts of people were gathering, and we had science discussions and policy discussions and all sorts of stuff, and celebration about the New Horizons mission. But what's impressive here is actually about a quarter of the team were women, which is a pretty high fraction for space missions, and is certainly a lot more than most other nations have. So we took pictures. Okay, and then we were finally told, this is Alice Bowman, the mission manager, who told us that the spacecraft was well and full of data. It had phoned home in the same, and you know, it really was a momentous occasion similar to the Apollo era with the landing on the moon, but a different mission, but similar enthusiasm, and we jumped up and down with this is kind of embarrassing picture, but that was sent around the world, and people have sent me that this appeared in newspapers in Malaysia, but enthusiasm was real. It was the fact that the data banks were full that really, that was important. So what did we see? We started to see these pictures. These were some of the early pictures that were sent down. We really began to see not that boring object with just a few impact craters, but a whole bunch of geological features that we really were beginning to work out what was going on. Remember that if we have a 6.4 Earth day spin period, we're only going to see in a 4-hour flyby one area in high resolution, and we chose the bright area on purpose because that meant it would be shorter exposure times, right? I mean, we didn't know it was going to look like a heart. I mean, big PR, etc. Hoo hoo, ha ha, very funny. But what was important for us was the fact that we could take pictures of the bright areas quite easily, whereas the dark areas weren't so easy. You'd have to have longer exposures. So that's why we picked that side, which turned out to be a lot of luck. We do have more pictures of these other areas, and they are coming down slowly over time. It'll be October before we get all of the data down from the spacecraft. So this is an early map of Pluto, and you can see this area that's well resolved. We have dark areas and light areas, and then these fuzzy areas that we don't have so well resolved. So what's it like inside? We have to keep this in mind, that if we're roughly, it's actually more like a third ice, 2/3 rock, but this means that you've got something like a 300-kilometer thick water ice layer. And at these temperatures, about 40 Kelvin, this ice is like rock. It's really very rigid. Water ice is very rigid at these temperatures. On top, there's a dusting of other ices. Okay, so when you're looking at this surface, it's ice. Mostly water ice is the most rigid, but also nitrogen, methane, and CO ice. And indeed, this white patch, which became called Sputnik Planum informally, is mostly the more volatile ices. So let's talk a little bit about, this is a flyby movie showing you how we came in, we flew by, we took these high-resolution pictures of Sputnik Planum here and then flew by. And then we did solar occultations and Earth occultations, the radio instrument of both Pluto and Charon. And this was very important for understanding the atmosphere. So I'm going to sort of go from the outside inwards in terms of looking at the science. So this is the UV Stellar Solar Occultation, and if you look at the white lines, these are the data coming in and going out, the sunlight going by. You'll see that there's a lot of absorption out here, and then deeper absorption here. And the red lines are actually reversed, and so you can see the fact that the going one way and going the other way look very similar tells you this is a very symmetric atmosphere. So there's absorption at high altitude and lower down. Higher up, we're seeing nitrogen absorption. then we see methane absorption, and then we see hydrocarbons deeper down inside. Indeed, when we look at the surface pressure, we're getting surface pressures of about 10 microbars. So it's a very low atmosphere, billionth of the Earth's atmospheric pressure. But there are some asymmetries, is the fact that there's a higher pressure, that it's colder here where it's white, and the albedo is lower here, maybe explaining the difference in temperature and slight differences in pressures near the surface. And most of the pressure is nitrogen here. Now, this was the prediction of what the absorption would be as a function of wavelength in the UV, and it was expected that most of the absorption at the shorter wavelengths would be nitrogen, N2 absorption, similar to what you would get in our atmosphere, though at different pressures. And then we would expect to see methane and hydrocarbon absorption at longer wavelengths. What was actually observed is much less absorption higher up, and so this suggested the amount of nitrogen was much lower than predicted. And this was a big mystery. What happened to the nitrogen? Where did it go? Well, here are some clues. When we look back at the sun through the atmosphere, we see these hazes. These are different wavelength. This is observations. But what's interesting is, yes, you have a sort of blue scattering, which suggests Rayleigh scattering, like the Earth's blue sky, which suggests relatively small particles. But there's also some scattering deeper down, that is at longer wavelengths, which suggests also there's me-scattering. So you've got both. So maybe we need to have, the current idea is that maybe there's some sort of fractal structures, the aerosols, that are many layers of aerosols, which I'll show you more pictures of in a minute, are made up of these hydrocarbons that are sort of mixtures of hydrocarbon molecules held together in a larger, into larger structures. At least that's the current idea of what's going on. So when we look at these hazes, you can see here the haze layers, and in fact, it's not so clear in this presentation, but the layers of hazes are quite substantial, multiple layers at different altitudes. So what do we think is going on? Well, the idea is that UV radiation is interacting with methane, and the net result is first to produce ethylene and acetylene, and then hydrocarbons, which are often called by planetary scientists tholins, for want of a better word, which are really just complex hydrocarbons. So this is sooty, black, dark material that is raining out of the atmosphere. Yes? Yeah. Why is it what, sorry? It's okay, so the question was, why are we seeing the blue light, the scattering, the Rayleigh scattering? That's really the size of the molecules that produces the color, dictates the color. It's at the short end of the visible part of the spectrum. And that is, those are the smaller molecules like nitrogen, methane, and the smaller hydrocarbons, okay? And then what happens is those hydrocarbons accumulate to make larger hydrocarbons, and they make more complex hydrocarbons that are then bigger molecules, which scatter at longer wavelengths, but also rain out of the atmosphere. So we can see these spectroscopically, both from the New Horizons spacecraft and also from Earth. So I'll come back to that in a second. I know this is a little difficult to read. This is Darrell Strobel's plot of the atmospheric constituents, and as Darrell likes to make things more complicated than they need be, let me just show you. This is density in this direction. So if we think of things like methane, which is the red profile, is like this, with these constraints by the data here. The nitrogen is here. And then the upper scale gives you temperature. And what we were expecting is this dashed line that would have high temperatures of about 110 Kelvin, which is pretty hot, for this part of Pluto compared with the surface where it's down at about 40 Kelvin. We expected to be much hotter higher up. What we found was the temperature was closer to 70 Kelvin in the upper atmosphere. And this explains why there's much less nitrogen. It's much cooler, it's much more confined lower down. The scale height is smaller. But then why is it colder at these altitudes? You'd think that with methane being a greenhouse gas, it would be a lot warmer and so on. And it turns out that we think that hydrogen cyanide and other hydrocarbons are cooling, are radiating out and cooling the upper atmosphere. And we have good reason for this, not only from the ALICE data on New Horizons, but also, it turns out, the ALMA telescopes, which are microwave observations that are made, I think millimeter wave, in Chile, a new astronomical observatory array that has been coming online relatively recently, have been making observations of Pluto and finding, indeed, very good spectroscopic observations of hydrogen cyanide and other hydrocarbons at high altitude. So this was completely unexpected, but these ground-based observations are sort of happening around the time of the flyby, and we're beginning to put together this picture that the upper atmosphere is cooling off, radiating to space with this material, hydrogen cyanide. And so this means the upper atmosphere is much more compressed and not expanded out as much as we thought. So maybe one of the solutions to Earth's climate problems is that we need to put hydrogen cyanide in our upper atmosphere, maybe? Actually, it would break up, so it's not a solution. Don't worry, I'm not advocating it. Okay, so the implications of this is that we were going into this flyby thinking that Pluto had an atmosphere that was very extended, and so we thought its exobase would be about 8 Pluto radii. And indeed, when we fly by and we make the observations, it turns out that it's much smaller, something more like 2.5 Pluto radii. That's still pretty big compared with, say, with the height of the exobase on Earth. But this had big implications for the solar wind interaction with Pluto. And this is what I was involved in the mission to study, is to look at what would we see as we flew by with the particles and fields instruments. And what we were expecting was a very puffy atmosphere, escaping atmosphere, similar to a comet with very kinetic plasma interactions of the solar wind, which is quite tenuous, and the weak magnetic field out here at 33 AU, we expected to see a comet-like interaction. And indeed, we made predictions based on the solar wind flux. We used typical Voyager observations. The predictions were a huge range of size of this interaction, from about 1 Pluto radii right near the surface out to 1,000. We were hedging our bets. It turns out that, first of all, when we flew by the solar wind, there had been a compression region in the solar wind that had come by a few days before, and so the flux was particularly high. And then on top of that, the low atmospheric temperatures at high altitude meant that Darrell Strobel dropped his estimates for atmospheric escape. He, in fact, dropped it first by 4 orders of magnitude, brought it back up by 2 orders of magnitude, and now it's sort of settling down at around 6 times 10 to the 25, mostly methane rather than nitrogen escaping per second. So this is much less than a typical comet. So it's much more, in fact, more like Mars, which I'll come to in a second. So what did we see with the solar wind around Pluto instrument from SWIRI? Well, if you look at an energy time spectrogram, you can see the solar wind up here with protons, and then helium alpha particles up here, and then interstellar pickup ions. And we have flow speeds, densities, and temperatures that are very typical for the solar wind at these distances. But the problem is that there's an area in between these gray areas, which are not so easy to see, but you can maybe get a sense that there's patches in here. And those damn cameras, right? So the cameras are going, and they're going click, 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 taking pictures all over the place. In the meantime, the solar wind instrument, which is supposed to be looking at the solar wind, is being flung around because of those cameras, right? So it's really difficult to analyze these data. We were expecting an interaction region that would be in the next room, the scale of which would be in the next room. And so this is a much smaller interaction region. And it turns out we probably missed the bow shock because the spacecraft was busy taking those pictures. Well, that's the way it goes. So we can say, however, that there are two locations. A location A, where we know there's less than 1% slowing of the solar wind, so we can sort of put a range of, we can bound the size of the interaction region, and then we can say there's a region where we have about 20% slowing of the solar wind. So somewhere in that range is where we would have had something like a bow shock or an interaction region starting to take effect. So if we then put this on a scale of Pluto and its atmosphere, and we have the spacecraft coming through like this, then this is the region where we have very poor observations because they're busy taking pictures. So we know that the bow shock is probably somewhere between these two. The upstream conditions has a Mach number, it's about Mach 40 flow out there in the outer solar system. It's a very cold, high kinetic energy flow. So if you had a Mach 40 shock, it would look something like this. If it slowed down upstream, then you'd have a much lower Mach number. So we just put that in our science paper as the bounds, current estimates of the Mach number. Okay. The simulations using Darrell Strobel's current escape rate. These are hybrid code simulations from Peter Delamere. And we get something here that looks a bit like this. It's a very kinetic interaction with a lot of instabilities on the boundaries, with a tail behind of heavy ions that are being stripping off the atmosphere and carried downstream, which is somewhat consistent with the observations that we're seeing, but we have to really do a detailed comparison before we say conclusively what this really interaction is like. But the conclusion is quite an interesting one. Hanging out at LASP, there's all this fuss about MAVEN at Mars and Mars this and Mars that, and all the MAVEN excitement, you know, all the team are getting excited about it. And so they're showing off all their papers and results. And then I realized during their press conference, you know, if we take Pluto's exobase, the smaller one than originally estimated, we put it on exactly the same scale as Mars, you can see they're actually about the same size. And so, of course, the solar wind is much weaker out here, but it's about the same molecular escape rate, and the size of the interaction region is comparable. The magnetic field is much weaker at Pluto, and so you have a much more kinetic, puffier, if you like, interaction region. Okay, so that's the atmosphere and the solar wind interaction. Let's look at the geology, which is the cool stuff. So we have our dark region over here, light region here. We have sort of mixed mottled region in between. And when we look in color, what we see is, when we look at the spectral features, we see that we have this lighter region. We see CO ice, nitrogen ice, and some methane ice, whereas you see the dark region, there's not a lot of stuff there. And indeed, that's actually where we see the water. So the water is absent from the Sputnik Planum, the very, with all the volatile ices, but forms a background for the majority of the surface seems to have water ice with black stuff on top of it. So that black stuff, or browny black stuff, is the tholons that are raining out, these aerosols that are produced in the atmosphere, raining out and coating the surface, maybe further radiolysis by cosmic rays, further turning this hydrocarbons into dark brown, gunky, oily, yucky stuff on the surface, these older areas, which have a lot of impact craters, are telling us that it's old and covered with gunk. If you zoom in, you can begin to see this is what it sort of looks like. There's some tectonic cracks, maybe due to expansion on cooling. But also you'll see that there seems to be sort of white edges to some of these impact craters, as if the high altitude regions have frost. And the idea is that perhaps methane frost, which is transported over the seasons from north to south hemispheres, you end up coating these high altitude regions with methane frost. Okay, so when we look at Sputnik Planum, which is this large region that is very white, if we zoom in, we can begin to see that there are various polygonal features, these polygons, which are thought to actually be areas where the ice is convecting. So this is solid convection of nitrogen ice. Now, nitrogen ice is much more, has low viscosity and will flow much more easily at these temperatures than water ice. Remember that water ice is extremely rigid at these temperatures and doesn't flow. It acts more like the solid mountains that stick up in between. And so the idea is, and this is a paper by Hammond and Barr from a couple of years ago for one of the icy moons of Jupiter, but the idea is that you can simulate this convecting ice with turnover times for this ice that are on the order of 500,000 years. So this is geology, long-term turnover, which seems, compared with the atmospheric processes and so on, quite long. But in terms of geological timescales, this is really active geology. This is recent turnover. And indeed, there are no impact craters that have been observed on Sputnik Planum telling us that it's a really young surface, consistent with this 500,000 year turnover time. What's interesting is that when you zoom in and you look at these convecting cells, you get these sort of chunks of what are probably water ice that accumulate at the places where the junctions where these convection cells merge together. And you sort of seem to get these chunks of ice there. And this is the boundary to the Sputnik Planum. This is a strip here of observations going from very young surface to old surface. And you can see these chunks of water ice which are sticking up. And these are quite large. These are as big as the Rocky Mountains, and they're water ice mountains, very rigid blocks. When you zoom in on these polygons, you can see nitrogen ice flowing into these off the plane into the older regions around, and you can see it flowing around obstacles or flowing into valleys and so on. So this is true glacial behavior with, on the edge of this big glacial area, you see the water ice mountains sticking up in between. And then there are things like this. This scale, this is about 20 miles. So we have these pits. Anybody have any clue what the heck they are? They're probably, each of them is about the size of this building or maybe a few blocks. Any idea? Wormholes, yeah. I think that, yeah, absolutely. It has to be, right? I mean, what else could they be? Well, here's some more. Look at these. So we're used to some of this phenomena. If we think about behavior of ice that have been sitting out for a long time, say all summer, we see these sort of sun cups and penitentes and so on. But we're used to a high solar flux and relatively volatile water ice in our case, and it's exposed over a relatively short period of time. What you have to think about is the role of sublimation, which caused this, happening over millions of years on a total expanse of ice, right? And maybe what's happening is that if you had a mixture of nitrogen and, say, methane ice, with methane ice being more volatile, or CO, then you have pockets of the more volatile material coming out. And you have to now think about sublimation effects that occur not over a day or weeks or even years, but over millions of years, producing these features. So a lot of these features may well be sublimation, just evaporation off the surface. Okay, so this is a totally new, no one was really thinking about this. The science teams have been turning themselves inside out trying to work out what's going on. And so we're seeing geological features that are totally unexpected and really making us think about how can you have geology on a surface that's at 40 Kelvin with ices that we really haven't got lab data for what their viscosity is at 40 Kelvin, let alone if you mix in a bit of other impurities, how do they flow and how do they behave? So here's just another example of a strip of data taken on the boundary of Sputnik Planum here, going through this blocky icy region into the older cratered terrain, and you can see you're going from these polygons to big blocky mountains to plains with covered in impact craters. So we can do some basic geology looking at this and trying to work things out, but I think it's going to take some time to really understand in a quantitative way how these surfaces have got to be this way. So this is an altitude map showing you high altitude blocks of ice here, lower valleys in between here, impact craters and so on. This is a very different sort of geology than we're used to here on Earth, or indeed of any of the other icy objects that we've explored in the solar system. Very different materials. Here is a nice strip showing you, again, from this area of the plains with these wormholes over towards a more rigid area where there seems to be some really strange features. And the geologists are calling these ice volcanoes. What is an ice volcano? Any ideas? I mean, I don't really know what an ice volcano is. It's tidal heating? No. Oh, yeah, you would think that because of this, you might have tidal heating. No, it turns out they're rigidly locked, very rigidly locked. There isn't any tidal heating to speak of between these two. Yeah. Maybe deeper down at higher pressures, you can lead to, you can lead to water ice or even nitrogen ice that might become volatile and come spewing out. Yes, indeed. But what is the equation of state at 40 degrees Kelvin of water ice and nitrogen ice mixed with gunk? I mean, we don't know. So, yeah, I mean, these pictures provoke us into thinking, well, there has to be something like that happening. But quantifying it's another question. Yeah. You would love to know what the temperature gradient is inside. That's going to have to be modeled because we don't have observations. So to know the equation state, it's going to have to be modeled because we don't have observations. What we do know is that Pluto and Charon have a very spherical, there's very little oblateness, and so that sort of suggests that they're probably pretty rigid, or they cool down to being rigid before they, let me think of the right way of putting this. They can't have been spinning a lot when they cool down to become rigid. Okay, let me come back and talk about the effect of the moons later. Okay, this does not look like an impact crater. This looks like material that's come from the inside, spewed outwards. The surface, a lot of the surface looks like impact craters. Okay, now we have another weird structure. This is about 300 kilometers across. These are large ridges. What could they be? Pressure here is 10 microbars. There's not a lot of wind. The idea that you would blow stuff around with that microbar pressure actually makes the Martian, the scenes on the Martian of doors being blown away on Mars even believable at that rate. Which is not. I mean, the pressure's not enough on Mars to do that. So if they're not enough on Mars, they're not going to do much here either. So probably it looks like it's wind driven, or again, this could be methane ice. But the difficulty you have to think about is the seasonal effects. I'm not going to go through all the details, but think about it this way. If the sun is over there, we first detected Pluto when it was going like this, with these going in front and behind. And so you can see that that is equinox. Both sides of Pluto get covered with sunlight, right? There's no permanently dark region if the sun's over there. Okay, now, at the time of flyby, keeping it oriented the same way, we're more like this. So we have some permanent darkness about 40% is permanently dark. And but it's because it's tilted on its side, you know, where is the hottest part of the planet over the season? Over its year, how do the seasons work? Remembering that it was closest to the sun when it was here at 30 AU, and when it goes all the way around to the furthest point from the sun at 50 AU, it'll have a completely different geometry. So the seasons are quite complicated, and it turns out the equator is where its average temperature is coolest, and the mid-latitudes have the biggest temporal variability. I mean, it's completely difficult to do in your mind. So think about seasonal effects, and you have migrating ices and frosts over the surface of these volatile materials being carried around. So again, this may actually be sublimation as much as it could be wind. Okay, so let me show you some of my favorite pictures. Here is a picture looking back towards the sun. We have haze layers. These are the mountains sticking up. This is Sputnik Planum. If we zoom in a little closer, you can see there's illumination backscattering by these layers of haze layers. This is the rough ice on the surface of Sputnik Planum. These are the polygons over here. These are the big blocky mountains that are sticking up by about 3 kilometers, 5 kilometers in altitude off the surface. So, I mean, this is a really quite complicated geological surface, much more complicated than we originally thought, and all sorts of interesting stuff occurring with materials which we really don't understand at all. None of that material is rock. Yes, absolutely. None is rock. The rock is 300 kilometers deep. Okay? It is not easy for us to get our minds around. This stuff is ice. Yeah. Sharon gets short shrift. It has impact craters. It has cracks due to cooling. A mysterious brown spot, maybe material that's come from Pluto, though how one does that, it's hard to imagine. It's mostly water ice. It doesn't seem to have volatiles. But at eighth the mass of Pluto, it would not retain those volatiles. And no atmosphere. When we look at the stellar occultation, it just turns off and on. So perhaps not quite so interesting as a moon. The little moons, these are the smaller ones. This is Sharon for scale. And then these are the smaller ones. This is a color one of Nick, so you can see some. These are not big enough to have enough gravity to pull themselves and to be round. But check out this. These are their orbits, and you can see this is Pluto and Charon that are phase locked, so you see the dot keeping the same side. And then you get things like this. These are from the light curves, strange shapes and rotating around. So how they got to be that way is hard to imagine. Something must be exciting these spins. It's hard to imagine how that got to be. We did not find more moons. We did not find dust. There were only 6 extra dust impacts over the flyby. So, you know, it's not as if there's a whole load of extra dust in this environment. It doesn't look like a recent collision. Explain that, will ya? Okay. Orientation. White spots are orientation. Yeah. That's just to give you a sense of, yes. Yeah. No, not actual white spots. Yeah. Good point. Okay. Okay, so here we are. We've flown past Pluto, and now we're heading out. And remember, we were flying through out in the direction of the Milky Way, so it's really hard to find capable objects in that direction. We used a whole bunch of Hubble time. We did find a candidate. We called it Jim Green, the head of planetary science at NASA. There was a lot of fuss about not giving things names because of the IU and the blah, 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 blah. So in quotation marks, this no one seems to object. And hopefully he will give us money to do an extended mission. Yeah, of course. I mean, yeah. So it's actually called 2014 MU69. I think it should be NW69, and then you could sort of tip it upside down and it'd be the same. No, never mind. So for scale, Pluto is an exercise ball, then Jim Green is a marble or a golf ball. And we have no idea what it looks like. This is an artist impression that is probably completely wrong, but it's about 30 kilometers across. So the important point here is we will be looking at an object that is radically different from previous objects we've explored in the inner solar system. And Pluto and Charon up here, this is size, kilometers, versus distance. And so you'll see we'll be looking at one of the smaller KBOs, perhaps less altered, probably less altered than Pluto and Charon, and we'll get a sense of what it's made of and what it's looks like and how the surface may have changed. So that's the plan. It's been quite a ride. We're going to fly by this is actually going to happen. The flyby of this object is going to be the January 1st, 2019, the New Year's Day. So we'll have another gathering to see what we'll see. So thank you very much.
Thank you for an excellent talk and questions.
How close are you going to get to the Jim Green object? Will the images look like those little small moons of Pluto, or will they be high resolution?
We don't know how close we're going to get. We're going to try and get as close as possible to try and get good pictures. And again, there's this issue, though, of smearing. So we're going to have to think about, we can't do active steering. We're going to have to just take the pictures. But I suspect we'll get the same sort of pixel, the same sort of scale. Yeah, that's the plan, anyway. Uh-oh, Michael's frowning.
There were several straight structures that we saw in various pictures, and I was wondering whether they could be either cracks or otherwise rivers.
Right. Okay. Getting anything to be liquid at 40 degrees Kelvin is difficult. It's possible that if you have to, okay, so liquid nitrogen is about 70 degrees Kelvin, so you'd have to warm it up, quite a bit. But you've got a lot of greenhouse gases in that atmosphere, and you can imagine over the seasonal, and don't forget there could be Milankovitch cycles, so that variation in the tilt of the spin axis. It's possible that it could be a lot warmer at times. I've asked the geologists that. They sort of laugh at me, but I'm going to persist with it because some of them do look river-like. But of course, you can have glaciers. These could be glaciers. You could be eroding the water ice, which acts like rock, with more volatile ices like nitrogen and methane. So I think there's a combination of rifting associated with cracking on freezing, with some possible, we have to get the topography right to know what's up and down to see what could have flowed one way or flowed the other way, right? You can't have, even glaciers can't flow uphill, so you have to sort of work out what's up and down. Yeah. Talking of which, I have a bunch of 3D pictures and some 3D glasses. So let's look at these, pass them around. Michael.
You were mentioning that this white area is young due to possible convection, and you were referring to actually a simulation that was done on that
Callisto.
convection.
Yeah.
How deep
Ah.
are the convection cells, and what is the assumed temperature at the bottom of those cells?
So they're thought to be about something on the order of 4, 5 or so kilometers thick, something like that. And so then comes this question of what the temperature is. Well, you don't need to have much temperature gradient between the surface and the top to drive this very slow convection, remembering that nitrogen ice is actually quite low viscosity and flows relatively easily. So the idea is you don't actually need to have a huge additional heat source, maybe just primordial radioactivity from the interior and the rocks. And remembering you've got 300 kilometers of water ice, which is a pretty strong insulator, thermal insulator, keeping a lot of that heat in. So you only need to allow a relatively small amount to leak out to drive this sort of convection. So it's not impossible to do it, at least that's current thinking, with just radioactivity in the deep interior, in the rocky interior, heating the lower layers of this nitrogen ice. Where's the microphone?
Whether with those differences in pressure and temperature, whether any kind of complex chemistry could arise from that.
Oh, you want to know if there's wiggly worms underneath, deep down in some ocean? There is, some people have postulated that there could be a liquid ocean at the rock water interface, right? I think it's a fantasy because it's so small, this object, it must have cooled off to the point where probably it's all solid. But indeed, you need to know the equation of state at these strange temperatures and pressures. And water, you know, it's got like, 12 different phases? I mean, who knows what phases this, we certainly don't have measurements at these temperatures and pressures, so, you know, who knows what it's really doing down there. You know, it's fine to keep thinking we're going to have wiggly worms down there. I don't think we're ever going to go down and find them. Go to Europa if you want to find wiggly worms.
Fantastic stuff, Fran, thank you. Cantankerous question. How many models have fallen full of these beautifully resolved observations? Can you count?
How many models? I haven't counted them, but I think certainly all of the team. So I'm sort of theme lead for particles and plasma and dust, and all of our models are no good. True of chemistry, true of atmospheres, true of geology. Yeah, they're all wrong. But that's cool, right? I mean, that's fun. That's great. It's great.
That's discovery. So when do we expect the next textbook to come out then?
Well, we are going to get all the data in by the end of October-ish. There will be a data analysis program. We're going to have a conference with a book that will come out in a couple of years' time, 3 years' time. But some of that depends on whether we get our extended mission funded, which I suspect we probably will. Oh, wait a minute, there's some more. Hey, check this one out. I got a couple more. Sorry, you got to look with the. This is one of the best ones, right? With the 3D glasses. Have a quick look.
More questions while you're watching?
I want to know when the IAU is going to apologize to the New Horizons team.
I have a question. You don't have to go back to the slide, but there's a picture you showed that it looks back at the sun, and the atmosphere is really layered. You see
The layers of haze, yeah.
Are those discrete particle?
Yes.
Ice layers? Or?
Those are haze layers of aerosols, and they are these are these hydrocarbon layers of hydrocarbons.
Okay.
Yeah. It's not ice, it's hydrocarbons. Yeah.
Oh, interesting.
Why do they form layers? Good question. You tell me. Here's another one. Oh, yeah, sorry. Okay. Well, we don't know. I mean, you know, we're still trying to understand the radio. We haven't got all of the occultation data down yet, or the composition data. Those are the sort of things. We took the pictures down first, obviously, to keep the public happy, and then we're now getting the more detailed solar and stellar occultations. Yeah. Okay, so how on earth would we know whether there's electrical or magnetic activity? No, we did not carry a magnetometer. Do you want me to show you the slides that I showed at UCLA? Because I knew those guys were going to grill me on this. Do you want to see them? Okay. Okay, so this is, I will come back to these pretty pictures. I've got some pretty pictures. Blah, 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 blah. Here we go. Okay, so if you measure the magnetic field using Voyager, this is the average sort of, you need to measure 0.1 nanotesla at 33 AU. Okay, that's what you need to measure. Okay, so look at Voyager. Voyager had a 13-meter boom onboard outboard magnetometer that weighed 5.6 kilograms. Okay, Cassini had 11-meter boom. Okay, and the instrumentation had gotten lighter by the time of Cassini. Okay, this is the size of the New Horizons spacecraft. We are not going to put 11-meter boom on this thing. Not and get it out in decent time. The total mass of the payload is 30 kilograms with cameras and all sorts of instruments. It's so hard to justify putting on the extra mass of a magnetometer and a boom when we don't expect there to be a magnetic field. The size of this core is about half the radius of the moon's core, and the moon doesn't have a dynamo. So why on earth would you expect this thing to have a dynamo? So forget it. We didn't put a magnetometer on. I regretted that enormously at Jupiter, but it was just not justified, particularly with a $800 million mission. Okay, end of lecture. Let's go back to, here we go. Check this one out. This is the Ice Volcano. Does that answer your question? If you take the size of the interaction region and you calculate what kind of surface field would you need to produce that, it's pretty weak. It's about 30 nanotesla. So, you know, the upper limit on any internal field is pretty weak.
Okay, no more questions. You're welcome to stay and enjoy the pictures. So let's thank
There's another one there.
Fran again.